Hello everyone, welcome back to another DDLC seminar. Today we have the honor to have Professor Kyriakos Vamvoudakis. Professor Kyriakos Vamvoudakis earned his diploma in Electronic and Computer Engineering from the Technical University of Crete in Greece in 2006, graduating with highest honors. He then moved to the United States and obtained his MS and PhD in electrical engineering in 2008 and 2011, respectively, from the University of Texas at Arlington, under the guidance of Professor Frank Lewis. From 2011 to 2012, he served as an adjunct professor and faculty research associate at the University of Texas at Arlington and the Automation and Robotics Research Institute. Between 2012 and 2016, he was a project research scientist at the Center for Control, Dynamical Systems and Computation at the University of California, Santa Barbara. He then joined the Kevin Crofton Department of Aerospace and Ocean Engineering at Virginia Tech as an assistant professor, a position he held until 2018. He currently serves as the Dayton Dukov and Dodd Professor at the Daniel Guggenheim School of Aerospace Engineering at Georgia Tech. His expertise is in reinforcement learning, control theory, game theory, cyber-physical security, bounded rationality, and safe assured autonomy. He has received numerous prestigious awards, including the 2018 NSF Career Award and the 2018 DoD Minerva Research Initiative Award. His work has also been recognized with several Best Paper nominations and international awards, such as the 2016 International Neural Network Society Young Investigator Award, the Best Paper Award for Autonomous Unmanned Vehicles at the 27th Army Science Conference in 2010, and the Best Researcher Award from the Automation and Robotics Research Institute in 2011. Last but not least, he is an associate editor for several journals, including Automatica, IEEE Transactions on Automatic Control, IEEE Transactions on Neural Networks and Learning Systems, IEEE Transactions on Systems, Man and Cybernetics, IEEE Transactions on Artificial Intelligence, Neural Networks, and the Journal of Optimization Theory and Applications. Professor Kyriakos Vamvoudakis, welcome.
Thank you very much, Pano. Thank you very much, Pano, Nisant, and Santing for this wonderful invitation. It's always great to talk to your lab, and thank you very much to Andreas for is being the big boy under this. So thank you. So today I will talk about. Let me actually put this aside. I will talk about how you can breach models in data and how you can use this information to enhance cyber-physical security and control. Okay, so we have been working on a theme that is called cyber-physical systems. Of course, it's a well-known thing where it's a combination of cyber components and physical components. Against cyber components are computation and communication, and physical components are actuators and sensors. And of course, cyber-physical systems are everywhere. That's why, as controls people working also on the security and resilience side, we need to get together and provide several contributions to this side of the world. So, of course, there's different kinds of techniques. Either you can use your model to do model design, model-based design, or of course, you can use other techniques that are more model-free, as you will see, or you can even combine both of them, as you will see at the latter part of the talk. So, of course, when I have a model and I know the exact model, I can verify system properties, I can identify vulnerabilities, and I can synthesize controllers, right? So this is very easy. I mean, considering that my model doesn't change, I can actually test the software and everything will work. But of course, in real situations, this is not what is happening. But we will use ideas for a model-based design to assess different properties of control systems and in the broader sense, cyber-physical systems. And finally, bring together interactive model-based and model-free controllers to enhance these capabilities. Okay, so let's go back to our Controls 101, and we will talk about some things that controllability, observability. So let's say we have a linear system, which is given by this x dot ax plus bu and y cx. Of course, everything is self-explanatory there, but let's say that X is the state, Y is the input, Y is the central output, and A, B, C are the state input and output matrices. Of course, it's classical when you want to check these fundamental properties of the control system. You check controllability, A and B is controllable, or observability, A, C is observable. But things are not easy to quantify when, for example, you have adversarial actors that can compromise and get you to the verge of controllability or observability, or even get you out of it. Okay? So, and then you will see that we have two things here as AX and AY. So this is how the bad actors, they connect into our system. And what we eventually want to see is we want to quantify something that we will call as distance to uncontrollability and distance to unobservability using knowledge of the model. And of course, we can use this to inform potential defender operator on how we can choose the appropriate actuator and sensors to improve resilience. Again, up to now, basic things. So again, this is one like schematic where you have some leaky side channel in the system that can expose information about the state. Okay, so for example, you have an attacker, which you can see with this skull face over here, that can observe a signal K of t. The signal K of t is a time-varying signal. Okay, and the K, the capital K, is the attack information channel. Okay, so again, this is a generalized scenario. You will see what exactly will happen pretty soon. Okay, so of course, if my bad actor, skull in this face, then can observe the full state, right? So the K signal is actually the whole state, right? If I can observe part of the state, so as you can expect, my K goes to C, and then I measure only the outputs. In other words, wherever I have sensors for whatever parts of my system. Okay, so why this is a big problem, especially when you're designing any control system, but in the broader sense, if you're designing cyber-physical systems. So, for example, you remember before you had two things that the attacker can check, can actually enter into the system. This AY, AY, and AX. Okay, so in other words, since the attacker is having this K of t, right, can scale this K to adversely design AX and AY that they enter into the system as you saw before. And then eventually you get these two AX and AY signals, okay? So AX has gamma AKX and AY is gamma CKX, okay? So again, you can think that one is attacking the state and the other is attacking the output, okay? So of course, what we want to eventually do here is we want, as the attacker, we want to find this gamma A and gamma C to drive, let's say for the first case, the closed loop system to unobservability. Okay, so again, we want to see how an attacker can design this gamma A and gamma C to bring it to unobservability. Okay, so again, what we have done here, again, pretty simple math. What we have done is we have substituted AX and AY that you saw in the previous slides. And then eventually we have this new system here. So eventually my A matrix is changed and becomes like a new A matrix, if you can call it. And my C matrix is changed and becomes a new C matrix. Okay. But again, now I want to design this gamma A and gamma C such that this pair is unobservable. Okay. So, of course, we will define something that we call as distance to unobservability, okay? And we will see how easy it is for the system, easy, I guess, or difficult, whatever you call it, for the system to be unobservable. Okay, so again, this is, I will say, a definition now, okay? So we want to design gamma A and gamma C such that this pair is unobservable. Again, pretty simple, right? Pretty simple. And I want to do the least effort attack, okay? So I want to find this set, omega, such that with the least effort attack, I define this gamma A and gamma C such that my system is unobservable. Okay, of course, as you saw, all my components that I have designed before, they're complex. Okay, complex numbers. Okay. Okay. And of course, people will say, okay, by using this complex, okay, so I used it just for numerical computations, because if I use real constraints, then I will have problems of discontinuity. Okay. But again, this is some math that if you're really interested, we can share some papers with you. Okay, so now what we will do is I will first check some algebraic observability formulation. Again, pretty simple ideas. So for AC observable, I give you some K and some gamma AC. Okay, so I want this pair to be unobservable. So what we do, we go back again to our controls 101. Okay, and then these are the two equations that they need to hold, right? Okay, of course, this goes back to the PPH test, right? Okay, so if such gamma A, gamma C, VSE exist, so I can write them like that. Okay, again, this comes from the all those things, they come from the PPH test. Pretty simple. Okay, so, but again, what I want, you remember, I want to find the smallest gamma A, gamma C in terms of such VNS. Okay, so this is our first theorem. So again, since I want to find the minimum one of them, right? So I just have to solve this simple optimization problem. Okay. So of course, you will see that I can do some tricks to reduce some variables, right? So you see this is over SV and this is over only DV. Okay. So what we can do eventually is we can find some bounds on the distance measure. Okay, so in other words, I can find by manipulating gamma A and gamma C what are the bounds that this will enforce or my observability. Okay, so I know that inside these bounds, this omega set that I find eventually, I am observable. Okay, so anything that moves me inside this bound, as you will see later, makes me observable. Okay. And one actually very interesting thing that we found is that this bound surprisingly doesn't depend on A. Okay, so it depends only on C and K, minimum and maximum eigenvalues. Okay, so now let's take some special cases of the attack information channel. You remember before I had talked about information when I have the full state information and when I have partial state information. So the first is full state access. Okay, so then I want to find this set. Okay, again, you remember every omega set has information of A, C, and K, right? So this K now is IN, which means that I have full state access. Okay, so then eventually I have to solve this optimization here. Okay, so we will take some special cases where if K is a column orthonormal, then you will see that this omega set doesn't even depend on K. Okay, so again, this is with a column orthonormal K. This is equivalent to the case of full state access. Okay. Now the third part here is when I have, I will say, partial information of the state, or in other words, I have sensors that they measure some parts of the state, not all the state. Okay. So again, we have the full state access. Special case where case orthonormal, where again these two are equivalent, and then the other case where I have information only about the sensors. Again, you see that AC, ACC means that the K is equal to C, right? And then if attacker, though, you will see something interesting another here. If the attacker can observe the output, then the set is not longer a function of A, C, okay? And then by changing A, C, it doesn't change the distance to observability. Okay? So you'll see some examples pretty soon. So again, we have computed numerically, and this is the optimization problem to solve. Again, this is the general one. And then we have added some small epsilon there for some relaxation, okay? And we use a descent-based numerical procedure. This is just the way to solve it. So you will see that the third part, the third line here is we're using the gradient of the cost. Then we compute the t, which is the step size, and then we update the v. Okay. So again, this is just a simple way to solve this optimization problem. You can use your favorite optimization technique to solve it. Okay. So let's see some examples. Let's say I have these following instances of system matrices. Okay. So remember, I do distance to unobservability. Okay. So I have this A matrix. My K is 2i, and I have these two C matrices. Okay. But you will see that in the C matrices, everything changes with phi. Okay. So I want to compute the omega set for AC1K and AC2K. Okay. And I will compare it to the theoretical bounds that I found before. Okay. So by theory, AC1K is between 0 and 1/2 for all phi. Okay. For AC2K, this is between 3/8 square root phi and 1/2 square root phi. So again, these are the theoretical bounds. Okay. So let's see now what happens in the simulations, and they're verified by the bounds. Okay. So you see that the omega C1K is between 1 and 1/2, 0 and 1/2. Okay. And then for AC2K, they depend on the phi, and then this is what you get. Okay. Okay, so these are the two examples for the two different omegas. Now let's say what effects do I have if my system A changes. Okay, so you see now that the A matrices, they have this theta there. Okay, so we will check what is happening if I vary theta. Okay, again, what you see here is that my C and my K, they're the same. Okay, so I have to find two sets, A1 CK and A2 CNK. But you remember before what I said is that it's independent of alpha, right? So you will see that the theoretical bounds there for both systems are the same for all theta. Okay? So these are your two distance measures. Okay? So again, the omega range for both of them, as you can see here, is theoretically proven to be between these two values. Simulation, they verify what we found in theory. Okay. Now, let's say the third part is what happens when you change the information channel K. Okay. So here, as you can expect, I have A and C are the same. And then what I do, I change the K. Okay. So, as you see, I will find my AC for all different Ks. Okay. So you will see that I will take cases, as you remember before, I have some special cases when K4 and K, when the case is column orthonormal, okay? And then you remember when it's column orthonormal, it doesn't like change, okay? And then you see it because K4, remember the I is when I measure all the states, right? I3. And then you see my Ks are column orthonormal, so K4 and K5, they're the same, okay? If I had full state access. And then the other ones you see, they change with a different case, okay? But yeah, so these are some interesting observations, which again, they're proven and everything is validated by our theory. Okay, of course, we have done other cases as well with different dimensions for A and C, okay? And then for every combination of N and P, we generated 100 random observable pairs, okay? We set K equals to C, and then we compute all the distance measures for all these things. And then again, these are just some, I will say, large-scale simulations that we did, okay? Again, for AC, when I have k equals to c, my omega set is equal to 1. Okay. Okay, so now, again, let's go back to 101, controls. You already know that controllability, observability, they're dual, right? So let's work out some parts for the controllability and you'll see what happens. Okay, so again, I have my system, and then the attack vector is this A, as well as this D, which is the attack input channel, okay? So again, the attacker can scale X and U and can design this A attack, okay? And again, in a similar vein with before, what I want to design the smallest lambda A and lambda B such that my whole system is uncontrollable, okay? And again, similar things with before, right? I mean, they're dual. So this is the distance to unobservability, to uncontrollability, sorry. Again, we solve the optimization problem. Of course, I reduce the decision values, and then I solve it using numerically as we had done before. And but here we took it one step further. Okay. So what happens, let's say, if I want to check this distance to uncontrollability, but I really don't have any information about A, B, and D, right? So, so in other words, what we have to do is we have to use techniques of, I will say, we have to learn A, B, and D, and eventually derive the distance measure, okay? So again, this goes back again to system ID. What we want to do is we want to design adaptive laws such that our approximators theta will eventually learn the real matrices A, B, and D. So again, these are some pretty simple ideas that we used here. So instead of having X, we have an estimation model, okay? And then the tuning law estimates to find the A, B, and D. They are derived by this tuning law over here, okay? So what we do here is we use this parameter identification to find the values of A, B, and D. Okay, and then of course, if I find the estimated values of A, B, and D, I can numerically compute the distance measure. Okay, so let's check some examples as we did before. So we have A, B, and D. You see that the A matrix has xi there. We take different cases for xi. We have these 6 different cases. For each xi, we identify A, B, and D, and then we compute this eta, which is the distance. Okay. Of course, the distance to uncontrollability, again, we can verify it theoretically, and then we will see eventually if in the simulations we will get the same results. Okay. Again, you'll see here that for all xi, even if I change the xi, the A matrix, it's also, again, pretty interesting, then the theoretical bounds are the same. Okay. So this is how we identified for different cases of xi. Okay, so we eventually find the A matrix here. We can do the same for A, B, and D. And then here are the distance measures. So you remember the bounds that we found before. Let me remind you, is 0.1118 and 0.2236. Boom, the same ones here, right? And then you see that the eta for each xi case is still in between these 2 bounds. Okay. Okay. So what we have done up to now is we used the system model to derive the adversarial distance to unobservability and controllability, and then we characterized bounds on these distance measures, and we got some special cases. Again, we shown how to demonstrate this in several examples. But I showed you a little trick that you can do system ID, but usually system ID is not always easy, okay? So usually what you have is you have information about the model, and then you can incorporate this information about the model, and then you have model-based and model-free techniques that they have to run together such that you can eventually learn the optimal solution, for example, okay? Or another case is, again, I have an aircraft. The aircraft flies. reduces fuel, so the mass changes. So then whatever I have computed before is not true for the new mass, right? So let's say if I have computed an LQR before, this LQR is for a specific mass. So, but when I fly the plane, the mass changes. So still the controller that I have computed offline is not optimal for this specific system. Okay. Again, this is, as I said, for accuracy when we need performance critical tasks. So let's go and talk a little bit about model-free methods. So these are two very famous, techniques that they can be used also in reinforcement learning, which are model-based and model-free techniques. Model-based methods are, for example, your LQR, right? Your LQR is doing computations offline. So in other words, it's offline synthesis. Of course, it's data efficiencies, but I told you it's suboptimal, right? Because again, imagine that you have a plane that changes your mass, boom, your new your controller is not optimal for a specific mass. Model-free methods, I will say they're more accurate. They can change in real time because they work online, right? And but of course they're more data intensive. Okay. So I want to bring together the benefits of model-based and model-free techniques. Okay, and then let's see how we can do that. Since we work on optimal control, we will take the special situation where we want to do optimal regulation. Of course, this can be extended to different cases. Another thing is that reinforcement learning and optimal control are the same in a sense. Again, one is offline, the other is online. That's why I think that using an optimal regulation problem will show the benefits of this approach. Again, we will actually first briefly talk about what we can do. So the first one is when you switch between model-based and model-free controllers, right? The other one is when you use model-based and model-free controllers concurrently. And the third one is when you use a model-based controller as an initial condition for the model-free algorithm. Okay, so our approach will actually be a combination of these two. Okay, the first two. Now, again, remember that I want to bring together the benefits of the two things, right? So, but remember, for the model-free situation, it's data intensive, right? I need to collect all this data, okay? So let's see how actually we can avoid this excessive data collection in exchange for tolerating some suboptimality, okay? So again, this will be a trade-off, as you will see, between accuracy and data efficiency. Now, let's actually start formulating the problem. Let's consider this controllable system, okay, AX and BU, and which you will see that A and B is unknown, okay? But I have a nominal model, okay? Let's say I have an idea about the system, okay? I don't know exactly what is the system. I have an idea about the system. So A and B here are unknown, but I have an available AM and BM, okay, which is known, okay? So again, I don't know how far are those, which I don't care how far are they. So again, I told you that I will do that for the problem formulation, for the optimal regulation. So again, this goes back to optimal control 101. So what I want to do is I want to eventually design a controller to minimize this cost function, right? And again, this X, remember, I have these two systems here, right? And I have to find this UP here to minimize this cost function, okay? But again, if I do it this way, still I'm losing something. So what we will do here, we will use a controller, which we will call it which will act on the system that has been synthesized offline using the model. Okay, remember, I have a nominal model. I will design a controller that will work on this nominal model first. Okay, but of course, the model is inaccurate, so whatever I have designed here will be suboptimal. Again, think of the scenario of the aircraft. Okay, so now, again, if I know the system exactly and the system doesn't change, again, my the model-based one, is good and it's not that intensive. and it will work out perfectly, right? But if at some time things are going to change, or the inaccuracy between the models is far away, instead of using only the that comes from the nominal system, I will use also an auxiliary model-free controller, okay? This is the utility that you see over here. And then this TS is a switch time where I switch between the model-based to something that we call as composite controller, okay? As you will see it over here, okay? So again, here I have my model-based, and eventually from TS and on, both of them, they work together, okay? So what we want to eventually do here is I want to determine this switching moment TS, okay? And if I determine this switching moment TS, eventually I will also find my U-tilted using trajectory data, okay? So U-tilted has to be somehow the model-free component that doesn't depend on the model. Okay, so now, again, here we have the value, right? Again, remember A and B are unknown matrices, okay? So if I go back again to optimal control 101, I can design my optimal controller that this is where this is the Kalman again here, and then this P comes from the solution to the Riccati, okay? So again, this is if I have the model, if everything is good, and so on and so forth, okay? But again, A and B is unknown, okay? So UP cannot be determined offline, okay? Instead, I have the idea of the model, as you remember before, right? I know AM and BM, so I will design this UM, okay? So this is the model-based controller. Again, this will come from basic techniques. Again, I will have this in my computer offline. I will compute this UM, okay? And this AM and BM, there's some ideas about the model that I have, okay? So again, AM, BM is the nominal model, so UM is null, okay? So from the two parts that you saw before, the two controllers, okay, UM is the model-based one, and now I have to design my composite controller that combines UM and the model-free controller. Okay, again, since my system is not exactly AM BM, I have a degree of suboptimality, which of course I cannot verify it yet, okay? So, so this is, let's say, if I was putting the system to the UM controller into my unknown system, AM and BM, okay, it will create one trajectory, right? And then another trajectory will be of the known model under the same control input, right? So here I have a model mismatch, right? So I have a mismatch of the system X, because it's the unknown system, and I have the one that will evolve if I knew the system and the system was not changing, or I will call it the nominal system. And this model mismatch, let's call it eta t for now, okay? So of course, if I want to check for the suboptimality, the easiest way to do is I take this difference, right? And then this difference eventually goes back to this eta, okay? Of course, this psi is how much suboptimality I can actually sacrifice, okay? But of course, this one, because I don't know this U star P, cannot be verified. So you have to find better ways to do that. So let's actually start thinking about switching things. The first thing that will come to our minds when we do switching is something like our folks in event trigger control have been using, right? So when you do event trigger control, you switch between closed loop and open loop, okay? So here, instead of switching between closed loop and open loop, we will switch between model-based and composite controller, okay? So let's see actually if the UM has a degree of suboptimality psi, then the Hamiltonian with this UM, again, this is just, I have substituted no, the things, nothing too fancy here, right? So you will see that instead because I don't have the optimal controller here, this is not zero, okay? So remember, if I put the star, then my Hamiltonian relaxes to Riccati, or for nonlinear system, my Hamiltonian relaxes to Hamilton-Jacobi-Bellman equation, which is equal to zero. But of course, here, this is not equal to zero, but it is bounded by this quality over here, okay? So again, this is still not good enough. So what we have to do is we have to find a better way, something that can be verified in real time, with something that you know, something that you can measure without having to sacrifice things. Okay, so again, we found this inequality using Lyapunov analysis. And if this has a degree of suboptimal xi, I can prove that the system has asymptotically stable equilibrium point given this inequality here. Okay. Of course, this can be checked, right? Everything is known here. So the xi is a degree of suboptimality. This is the minimum the minimum eigenvalues of Q and R. And then my state trajectory of the actual system, the unknown system. And is the nominal controller that I have computed in the past. Okay. So this is the switching moment, right? So the system switches from the model-based controller to the composite controller at this instant. Okay, so when this is equal, I switch. Okay. So again, these are for now we have designed our and we find the switching instant. Okay, so now we have to find ways to design our tilted. Okay. So now remember that every time that I am working with a composite controller, both of these controllers, they have to work. Again, I'm taking my unknown system. Remember, A and B is unknown. And then I'm using my composite controller, which is plus U tilted. Okay. So now I have, as you remember from before, I have a okay, where the is the known controller if I knew the model, right? So again, you go back, you can compute it from your Riccati equations. I can substitute it, and I have this using the Kalman gain. So equals minus R inverse B transpose P, right? So I can substitute it here, okay? So then my closed loop A system in this situation, given this has changed to this A tilted, okay? And then, of course, the B is the same. So now I have this new system that has x dot equals A tilted x plus B U tilted. Okay? So now I can use our favorite model-free off-policy reinforcement learning with graded convergence and stability. And then we can learn and use this and find this U tilted. Okay? So let's see how we can do that. Again, I want to solve this problem, okay? Remember, I had a V star before, now I have a V tilted, okay? And then the dynamics now that I have to do optimization over is x dot equals A tilted x plus B U tilted, okay? Again, this is the offline solution, okay? But we will learn this solution in real time without information about A tilted and B, okay? So let's see how we can do that. Again, very popular techniques to do that are policy iteration and value iteration. So policy iteration, you have to start with a stabilizing controller, and that gives you also a finite cost. Value iteration, you don't need to do that, okay? But of course, policy iteration is faster than value iteration with this small sacrifice. So what eventually policy iteration does is we start with a stabilizing controller with a finite cost, and then you solve this equation to find V, okay? Then after you find V, then you update your control policy. And you do that until convergence, okay? So this is the classical policy iteration, okay? But again, you see here that if I was doing that, my A and B are there, right? So instead, we have to use smarter techniques like off-policy learning or model-free integral learning. So in our lab, we have been using these actor-critic structures. So if we don't know something, what we do is we approximate it. I don't know V tilted. So what I do, I approximate it. I approximate it with a basis, with some weights and a basis function. Okay, and I do the same for my actor. Okay. Again, what eventually I want to do is I want to learn in real time this WI V and WIU. Okay. So this is, again, to learn this WIV and WIU, you can use your favorite optimization techniques. You can use least squares, recursive least squares. You can use gradient descent, steepest descent, anything you can imagine. Okay. And again, proving, you can prove that the cost every time decreases by using monotonicity proofs. Okay. And of course, also, we don't sacrifice stability. We also prove that the equilibrium point of the system is still asymptotically stable. Okay. Also, another thing that I wanted to talk about is that while you do that, in learning, you have to explore the state space, right? So this goes back to exploration exploitation, as well as in adaptive control, this goes back to something that is called persistency of excitation. So what you do here is you add some exciting noise into your control inputs, and then, for example, if your system has order n, you have to excite n plus 1 over 2 modes of the system. So you have to use that to has different frequencies. So all the frequencies that you use, for example, sinusoids, cosines, they have to have n plus 1 over 2 different frequencies, and they have to be linearly independent. And then and only then you can guarantee that you will converge to the real-time solution, to the optimal solution. Okay, again, here we used, as I said, the least squares, okay, to solve for the weights. But again, you can use your favorite thing like gradient descent or anything. Okay, so now let's see how this can work, okay? So let's say I have this linearized F-16 fighter jet with 3 states and 2 inputs, okay? My initial condition is 9 minus 615, and then I pick my user-defined matrices, okay? Again, you will see cases where A and B are unknown, are close, known, or different case. Okay, so again, remember, this is my A matrix, this is my B matrix. So let's check the first case when the system is inaccurate. Let's say one case we checked where your AM, okay, that I had, which is the nominal one, is 0.25 multiplied with A, okay? Again, everything that your actually real system, your nominal system is 0.25A, and then your B's are the same, okay? So what you see here is that you see the 3 states, and then the gray line is when I switch between the model base to the model free controller, okay? And then you see, because again, AM is equal to 0.25A, okay? So again, you see the control inputs here, and you also see the errors, okay? Again, remember that I switch whenever the threshold is over something, okay? And then this happens at the instant, I will say 1 second here, okay? So the first case is inaccurate model. And then again, here you see that I eventually converge also to the optimal solution, okay? So this is the learning component. So now, let's say what happens if I had a fairly accurate model. Remember, if I have a fairly accurate model, then I'm good enough. Why I have to actually use the expensive model-free controllers, right? So let's say now that my nominal controller that I had is close to 0.9A. Again, I have to remember that I have to pay a price for suboptimality, and I can actually tolerate some suboptimality, right? So you see here, if my nominal system was 0.9A, I'm still able to even not switch, okay? So the solution was good enough. Okay, and I think with that one, I will conclude and I will say that what we developed was a framework with interactive model-based and model-free techniques. We designed an optimality-based switching condition to switch from an initial model-based controller to a composite controller. And we computed this auxiliary component uh, using model-free reinforcement learning. And by the way, I will say that these model-based model-free interactions are based on a project we have with Professor Malikopoulos from Safe Learning Enabled Systems in NSF. And yeah, and then with that, I would like to thank all of you and also especially my student Surabi, who developed this work. And I will be happy to answer any questions.
Thank you so much, Professor. I have one question.
Sure.
Is there, what if we force the model to behave exactly as the real system through a model reference adaptive controller? And when we have these two behave exactly the same with this MRAC controller, can we do then, can we then do optimal control?
So let me see if I understand. So you know exactly the system?
I force the model to behave like the system. So the state of the model is the same as the real system.
So yeah, so then your LQR solution is good enough.
Okay.
I mean, if I have, let's say, if I can find a way to have the two states the same, so then I'm good with a model-based controller, and I will never switch to anything.
Okay, I see. Thank you very much.
And we have
Uh,
extended that to nonlinear systems, which, but I wanted to present here the closed form solutions because nonlinear systems they don't have closed form solutions. But yeah, I'll be happy to answer any other questions.
yeah, we have one question. Yeah, it's actually, how do people typically decide the basis functions within the actor critic settings?
That's a very good question. Okay, so for the linear case, because you know that the value is quadratic in the state, so you're sufficient to pick quadratic basis, right? If you have a nonlinear system, you don't know exactly. So what you do is the most you add, the better for you. So yeah, there's a compromise there. But for the linear case, that's why I presented the linear systems here, because I actually know that the bases are quadratic. For the nonlinear systems, you can use polynomials, and as many polynomials, the most polynomials you use, the better for the solution. According to Weierstrass approximation theorem, you can approximate any function with polynomials. But again, for linear case, you already know the basis.
Nice. One other question is, it seems like the presence of the adversary is
Mhm.
noticeable by the controller. Have you considered if the adversary wants to remain undetected, what controls they can take?
That's a very good question. Yeah, so if then the controller needs to remain undetected, so then we have to enforce some stealthiness consideration. We have worked on that one as well in the past. So in other words, let's say the scenarios that we approached was the Y that you see in the system and the Y after being attacked are the same. So this you can enforce a stealthiness approach, and the attacker actually wants to deteriorate your performance. Okay, so you still see the same outputs. Okay, so the attacker is stealthy, but your performance is being deteriorated by different techniques that we have used. Yeah, but we have worked also on that one. And actually, Surabi also has the student that she did all that. She has worked also on stealthiness, as well as my student Philippos has published a transaction automatic control paper on using moving horizon estimation and control to guarantee stealthiness and design from the two perspectives, from the defender attacker and attacker defender side, two games, and find what are the policies to solve this problem.
Another question is, Dear Professor, what assumption is required between the nominal mode matrix AM and the true system matrix A? Do we need boundedness type condition?
I mean, boundedness type conditions. So, of course, you can have infinity values in the matrices, but they can be random, as well as also they need to be the same dimensions. But we don't know anything else. So it's the only actually thing that we know is the dimensions of A and B, AM and A. They have to be the same.
Nice. I don't see any other questions.
Okay,
Do
can I ask a question?
Oh, yeah, absolutely.
Yeah, thank you, Professor Vamvoudakis. It was really interesting.
Thank you, Sam.
I just wanted to think out loud. So, we have in the second part of the talk where there is a model mismatch and we're switching between a model based and model thing. What if there is an attacker actively involved in this sort of setting? How should one go?
If it's an attacker where?
Within the second part of the talk where
Mhm.
you have the fuel is changing and in an airplane, but still there is someone who is trying to mess with the observations or so on and so forth. There is an attacker basically within the situation. So how do you envision what's gonna happen in terms of the system?
So let's say you have an attacker, and then the attacker actually can change your entries of A and B. So still can this work, because it doesn't matter what are the quantities there. So it can still work, but of course you will pay in suboptimality, right? So if I have another A, and then eventually my model-free controller is based on another A, but this other A is actually influenced by an attacker, so then I have to pay the price of suboptimality. So then you can use intrusion detection techniques, or you can use other techniques, so you can identify the attacker or sensor and actuators that they have been attacked, take them out of the system and continue operating, especially if you have redundancy. So these cyber physical systems, they usually have redundancy in sensor and actuators. So if you can find which ones they have been compromised to do this, what you said, so change your A and B matrices, then eventually you'll be able to still control the system in an efficient manner with guaranteed optimality that you control and not somebody else.
Thank you.
Okay, Professor, thank you very much for this talk.
Thank you very much, everybody. It's a pleasure, and I'm looking forward to see you in future conferences.
Thank you.
See you guys. Thank you very much.
See you.